Hello friends, welcome you all to the 16th lecture on functional analysis and its applications. In this lecture, we will discuss the set of all bounded linear transformation of nonlinear space n into n dash as a Banach space if n dash is Banach space. The content of today's lecture as follows. The set of all bounded linear transformation beta n dash of nonlinear space n into n dash as a Banach space if n dash is Banach space. Theorem: let beta n dash denotes the set of all bounded, that is continuous, linear transformations of a nonlinear space n into n dash. Then beta n dash is itself a normed linear space with respect to pointwise linear operations as t1 plus t2x is equal to t1x plus t2x and ATX is equal to A T of x, where A is any scalar. And the norm defined by norm T is equal to supremum of norm Tx such that x belonging to n and norm x less or equal to 1 are any one of the equivalents for norm T, given in the above theorem as discussed in previous lecture. Further, if n dash is Banach space, then beta n dash is also a Banach space. Proof: since normed linear space is defined on the linear space, so first we have to prove that beta n dash is a linear space. Okay. We know that the normed linear space is defined on linear space. So first we have to prove beta n dash is a linear space. Let T1 and T2 belonging to beta n dash, that is set of all bounded linear transformation. Then T1 and T2 are bounded. There exists a real number k1 greater or equal to 0 and k2 greater or equal to 0 such that norm T1x less or equal to k1 norm x and also norm T2x less or equal to k2 norm x for all x belonging to n. If a, b are any scalars, then for any x belonging to n, we have norm a t1 plus b t2 x equal to norm a t1 x plus b t2 x. Okay, because here in statement defined t1 plus t2 x is equal to t1 x plus t2 x. So here we can write a t1 x plus b t2 x. Again, as per this definition, ATX is equal to ATX. We can write this AT1X plus B T2 of X under the norm. Again, this is two term. We apply the triangle property of norm. So this can be written as less or equal to norm A T1X plus B norm T2X. Here A and B are scalar, so we can write this term as mod A into norm T1X and this term mod B norm T2X. Okay. So norm T1X and norm T2 x defined in equation 1, we can write this less or equal to mod A K1 norm x plus mod B K2 norm x. Okay, so norm x common, we can write mod A K1 plus mod B K2 into norm x, that is m norm x, where m is a positive constant as mod A K1 plus mod B K2. So norm A T1 plus B T2 x less or equal to m norm x. So A T1 plus B T2 as a bounded linear transformation. Okay. So we can say that A T1 plus B T2 is the element of beta N dash for all T1 T2 belonging to beta N dash. This proves that beta N dash is a linear space, that is vector space. Now we prove beta N dash is a nonlinear space. Since norm T defined as supremum norm Tx such that norm x less or equal to 1 in statement, and we know that norm Tx always non-negative, so we can write norm Tx greater or equal to 0. Hence norm T defined supremum of norm Tx such that norm x less or equal to 1, that is supremum of norm Tx greater or equal to 0, that is norm T greater or equal to 0. Hence first condition of norm is satisfied here. Second, if norm T is equal to 0, this implies that supremum of norm Tx such that x belonging to n and norm x less or equal to 1 is equal to 0, because norm T is defined this one. Okay. So this implies that norm T always non-negative, and if 0, then norm Tx is equal to 0, that is if and only if norm Tx is equal to 0 if norm T is 0. Okay, if and only if Tx is equal to 0. Okay, because norm Tx always non-negative. If norm Tx is equal to 0, if and only if Tx is equal to 0, that is T is 0 transformation. So here proved norm T is equal to 0 if and only if T is equal to 0, that is 0 transformation. Hence second condition of norm is satisfied. Third, if C is any scalar, then norm Ct is equal to supremum of norm Ctx such that norm x less or equal to 1. Okay, and Ctx can be written as supremum of norm C into Tx such that norm x less or equal to 1. And also we know that norm Cx, we know that norm Cx equal to mod C norm x. Okay, where C is constant and x is vector. So here Tx as a vector and C is scalar, so we can write this mod C norm Tx. Okay, with same condition norm x less or equal to 1. Here C free from the x, so we can write out of the supremum, that is mod C supremum of norm Tx such that norm x less or equal to 1. So as per the assumption, supremum norm T x such that norm x less or equal to 1 is norm T. So here norm Ct is equal to mod C norm T. Okay. Third condition also satisfied. Fourth condition, if T1 and T2 are the elements of beta N dash, that is T1, T2 are bounded linear transformation, then norm T1 plus T2 equal to supremum of norm T1 plus T2 x, such that norm x less or equal to 1. That is supremum of norm T1x plus T2x. Here norm of two terms. So we know that norm x plus y less or equal to norm x plus norm y. Okay. So we can write norm of T1x plus T2x less or equal to norm of T1x plus norm of T2x. Okay. So this expression can be written as supremum of norm T1x such that norm x less or equal to 1 plus supremum of norm T2x such that norm x less or equal to 1. Then first term can be written as norm T1 and second term can be written as norm T2. Okay. Hence norm T1 plus T2 less or equal to norm T1 plus norm T2. Therefore, beta N dash is a normed linear space. Now, we prove that beta N dash is complete because we have to prove beta N dash is a Banach space if N dash is Banach space. Let Tn be a Cauchy sequence in beta N dash. Then given epsilon greater than 0, there exists a positive integer n0 such that norm Tn minus Tm less than epsilon for all Nm greater or equal to n0. Okay, as per the definition of Cauchy sequence in beta N dash. Hence, for all x belonging to n, we can write norm Tnx minus Tmx equal to norm of T1 minus Tmx. Okay, because here defined in statement T1 plus T2x equal to T1x plus T2x. So norm of Tnx minus Tmx can be written as norm of Tn minus Tmx. Okay. Here Tn be a Cauchy sequence in beta N dash. It means Tn is a bounded linear transformation. Okay. So we know that if T is a bounded linear transformation, then norm of Tx less or equal to norm of T norm of x. So as per this definition, we can write this less or equal to norm of Tn minus Tm into norm x, which is less than epsilon into norm x, because here norm Tn minus Tm is less than epsilon. And also norm x equal to 1 or less or equal to 1. So we can write this is less than epsilon. So Tnx is a Cauchy sequence in n dash. Okay. Since n dash is Banach space, it is given in statement. Therefore, n dash is complete. That is Tnx converging to Tx, where Tx is the element of n dash, as n tend to infinity for all x belonging to n. Okay, meaning of this is Tx is equal to limit n tend to infinity Tnx for all x belonging to n. This defines the mapping T such that n to n dash. Tx is the element of n dash. Okay. So now we have to prove T is the element of beta n dash. It means we have to prove T is linear and bounded. Let x, y belonging to n and AB be any scalars. Then Tax plus By is equal to limit n tend to infinity Tn Ax plus By. It can be written as limit n tend to infinity A Tn x plus B Tny because Tn is linear. Okay. Here A free from n, B also free from n. Then this can be written as A limit n tend to infinity Tn x plus B limit n tend to infinity Tn y. Okay. Again, as per this definition, we can write this one Tx and this is Ty. That is Tax plus By equal to Atx plus Bty. This shows that T is linear. Okay. Now we prove T is bounded. We observe that norm Tx equal to norm limit n tend to infinity Tnx because here Tx defined limit n tend to infinity Tnx. So here we put the value of Tx. So norm as a function, so we can write as per the definition of limit of function, we can write this limit n tend to infinity norm Tnx less or equal to limit n tend to infinity norm Tn into norm x because Tn is the element of beta n dash, that is Tn is a bounded linear transformation. Okay, so this can be written as norm Tn norm x. This is can be written as supremum of norm Tn into norm x. That is supremum of norm Tn into norm x. Okay, equation 2. Also, we know that mod of norm Tm minus norm Tn less or equal to norm Tm minus Tn less than epsilon. Okay, why? Because we know that mod norm x minus norm y less or equal to norm of x minus y already proved in the chapter of nonlinear space. Okay, so applying this property here, mod norm Tm minus norm Tn less or equal to norm of Tm minus Tn. Okay, and also we know that from this norm Tn minus Tm less than epsilon. So we can write the value of norm Tm minus Tn less than epsilon. Okay, hence mod of norm Tm minus norm Tn less than epsilon. This is norm Tn is a Cauchy sequence of real numbers. By the general principle of convergence, norm Tn is convergent and hence it is a bounded sequence. So that we have supremum norm Tn less or equal to k. So from 2 and 3, equation 2 can be written as norm Tx less or equal to k norm x. That is this one. This shows that T is bounded. So here T is linear and bounded. Then we can say that T is the element of beta N dash. Okay. Finally, we show that Tn converging to T with respect to the norm on beta N dash. Here we have proved T such that N to N dash. Okay. So here T is the limit value of Tnx, and we have proved here T is the element of beta N dash. Okay. When N dash is a Banach space, and here we prove T belonging to beta N dash and N dash as a Banach space, then T is the element of beta N dash and beta N dash is a Banach space. Finally, we show that Tn converges to T with respect to the norm on beta N dash. Let epsilon greater than 0 be given since Tn is a Cauchy sequence in beta N dash. There exists an integer m0 such that norm Tm minus Tn less than epsilon by 2. For all mn greater or equal to m0. Okay. Let x belonging to n norm x less or equal to 1, then TLX converging to Tx. We can choose for some epsilon and a positive integer L greater than n0 such that norm Tx minus TLX less than epsilon by 2. Hence, for all n greater or equal to n0 and norm x less or equal to 1, we have norm Tnx minus Tx can be written as norm Tnx minus TLX plus TLX minus Tx. Here we have added TLX and subtracted TLX. That is Tnx minus TLX as one term and TLX minus Tx as second term. So this can be written as less or equal to norm Tnx minus TLX plus norm TLX minus Tx. Here Tnx minus TLX, this can be written as norm Tn minus TLX, okay, plus norm TLX minus Tx as it is, okay. So as per the definition of bounded linear transformation, norm of Tn minus TLX can be written as less or equal to norm Tn minus TL into norm x, and this term as it is. So norm x less or equal to 1, and from equation 4 norm Tn minus TL less than epsilon by 2, and from equation 5 norm of TLX minus Tx less than epsilon by 2, that is epsilon by 2 plus epsilon by 2 epsilon. So here norm Tnx minus Tx less than epsilon, okay. So this is norm Tnx minus Tx less than epsilon for all n greater or equal to m0, for all x belonging to n such that norm x less or equal to 1. Hence, for n greater or equal to m0 such that norm Tn minus T equal to supremum of norm Tnx minus Tx such that x belonging to n norm x less or equal to 1, okay, and this can be written as norm of Tn minus Tx such that x belonging to n norm x less or equal to 1 less than epsilon. So norm Tn minus T less than epsilon. It follows that Tn converges to T in the norm of beta Nn dash. Hence, we have proved here under the given norm also Tn converges to T. That is, beta Nn dash is a Banach space when n dash is Banach space. And the proof is complete here. Noting point, if n be a non-linear space, a continuous linear transformation on n into itself is called an operator on n. The non-linear space of all operators on n denoted by beta n instead of beta nn dash. Okay. In this lecture, we have discussed the set of all bounded linear transformation beta nn dash of nonlinear space n into a nonlinear space n dash as a Banach space if n dash is Banach space. These are the references have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Valley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publisher, written by B.B. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.